Welcome to our lecture on learning paradigms. So far, in the self-supervised learning, we have discussed about certain pretext talks, and then we have moved to discussing contrastive learning based self-supervised learning. There we have discussed, especially in this particular setting where we are not working in supervised setting, where of course it's quite convenient to create positive negative samples. However, in unsupervised setting, how do we create positive negative samples? Some possible mechanisms. And then we have moved to discussing some particular algorithms. Especially we started with SimCLR, and there, after discussing the algorithm, we started discussing about a few properties of its result. There, towards the end of last lecture, we have discussed how SimCLR, or rather most of these contrastive self-supervised learning algorithms, benefit from bigger models. That is, they show scalability with respect to the model size, and we have discussed why this is very important. When this is a good news, also what we see is that SimCLR requires large batch size to work. The reason behind this, if we want to understand this, study its loss function, how the terms are grouped in the numerator and the denominator, and you will understand why the large batch size is needed. However, what we would rather like to ask in this course to ourselves, is this a positive aspect or negative aspect that large batch size is needed? Take a moment to think about this. And what is the answer? The obvious answer is this is a negative aspect, right? Also, this leads us to the challenge: can we maintain a large set of negatives without huge batches? Why I am talking about this particular challenge, why I am interested in maintaining a large set of negatives? Because as I said, that the reason that we are needing this large batch size is mainly motivated by the loss function itself, where in the denominator of the loss function we need those negative terms, right? So if we could obtain this somehow without maintaining huge batch, probably we do not need the huge batch, right? Thus, the challenge is if we can work without huge batch of negatives, and going even a step further, we can revise this challenge to a new challenge. Can we even do away with the negative samples completely? This, at the first look, may sound slightly strange because how we defined the contrastive learning, of course, the definition itself involved having the x plus and the x minus, right? That is x and its positive paired sample x plus and then a negative sample x minus. Now we are saying, can we do away with the negative samples completely? Is there a possibility to do so? That would make our algorithm simpler, or rather our life simpler in many aspects, because then we don't need to think about really like, okay, what are the possibilities to obtain a negative samples, right? We will discuss these particular aspects in some of the future lectures in different context. However, at this point in the course, we'll skip discussing the algorithms next to SimCLR which took care of these particular challenges. What's important to understand at this point of time is that some of these successive methods actually took care of these challenges to some aspect, that they introduced particular aspects such as memory bank to do away with large batch size, and they introduced particular modifications in the architecture itself to do away even with the negative samples. So keeping those for future discussion, we have at this point in the course, we have got the basic idea of how contrastive self-supervised learning works, and that will be sufficient for us to go forward right now. So let us move ahead and let us discuss about yet another remarkable unsupervised representation learning mechanism known as generative adversarial network, or GAN. Motivate generative adversarial network, we need to think about two players who are always in competition with each other. Thus, when competing, both of them keeps on improving. Let us take some non-technical examples. The first example that we are seeing here right now is a fake currency example which was presented in the GAN paper itself. The idea is that you can think about a generative model like a group of counterfeiters who are attempting to create fake currency that would appear genuine, and thus to fool the discriminator, or in this case the law enforcement agency, who are trying to identify the fake notes. So as both of these sides continuously compete, what happens, at some point the generated counterfeits eventually, or at least that's what we expect, to become nearly indistinguishable from the real currency. Let us see yet another example. Think about the generative model to be a cuckoo bird that lays its eggs in another bird's nest, thus trying to make them appear identical to the host's eggs. The discriminator bird, in this case, you can think about, is the host bird, thus trying to detect and reject the foreign eggs. Through this ongoing competition, what happens is that the cuckoo evolves the better mimicry, while the host develops sharper detection ability. So we have so far seen some motivating examples which helped us to understand the two components of GAN, that is a generator and a discriminator. What is happening here? The generator is trying to mimic a data distribution, and at the same time the discriminator is trying to distinguish between the real data and the fake or synthetic data, that is the data that has been generated by the generator. This is inspired from game theory. So if you're interested, you can read about this particular aspect, about origin of the GAN or its inspiration in the game theory. However, in this course, we'll not discuss about that aspect much. So let us try to see a bit more pictorially what all we have discussed with respect to GAN. Given an input which we often call noise or even latent vector Z, the generator would produce GZ, and GZ is the fake or the synthetic data in this case, which means the discriminator now tries to predict, like if the discriminator function we denote this as D, we can apply this D on the GZ and we get D of GZ, and we expect a particular output for this D of GZ, and we could also feed X to D. What is X? Let us come soon to this. What is X? So from DZ we expect a particular output. Let's say this output is binary, and dx we would probably expect the opposite output, right? Why? Again, let us look at x. What is x? X is the real world samples in contrast to GZ, the synthetic samples. And that's why I'm saying the dx and the dgz, the output, our expectation is that, okay, if one of them is 1, the other is 0. And now, thinking about our objective in GAN, this can be represented with respect to this equation here, where the discriminator is trying to maximize this objective by correctly classifying the real and fake samples. You see here the objective function we are maximizing with respect to the D, whereas the generator in this case is trying to minimize this objective function by fooling with respect, fooling the discriminator, and we see the objective function we are minimizing with respect to G. So ideally, what happens is that if G and D have enough capacity and the training algorithm is followed, then the distribution of the G, this converges to the data distribution, that is, the generative model replicates the data generating process. So ideally, after sufficient training, what's happening is that G and D have enough capacity. They are reaching a point where P underscore G is equal to P underscore data, as you mentioned, and the discriminator is unable to differentiate between the two distributions. In some sense, the dx is becoming now half. For a fixed generator G, the optimal discriminator in a generative adversarial network is represented as this particular equation, and this particular equation, whereas we will not go for the derivations and all, you can easily visualize why I said that at this point the discriminator output will be half. because we said that the pgx will become same as p delta x, and then this will cancel out to the value of 1 by 2, right? What happens rather practically is that the generator and the discriminator, they do not have enough capacity to compete against each other, and in that case the training procedure doesn't proceed as expected. So this may happen in several ways, right? Think of this: a very strong discriminator, which means the generator is never able to fool this, and thus there will not be really any game between the generator and the discriminator. So this is one particular example. So in the same thing, if we think in the terms of our fake currency example, if the law enforcement is so strong, there is no real game between the counterfeiters and the law enforcement. In that case, there is no iterative improvement, right? So this particular case, of course, was just one aspect. There can be several other aspects, which means like there is no proper game or play between the discriminator and the generator. And considering such aspects, it's often seen that discriminator or the generator is intentionally weakened, which means one of them is updated more or less frequently, or different learning rate is applied for the discriminator and the generator. Thus, in a way, you can think of this is in a way you are compensating for one of the components being somewhat weaker, one of the component being somewhat stronger, to engage them in a meaningful game, so that from the feedback of the discriminator, the generator can indeed improve. One of the ideas in this direction is also introduction of a buffer of previously generated images and mix those with the current fake samples when training the discriminator. Why would we do so? Because this would prevent the discriminator from overfitting to the most recent generated outputs. Similarly, yet another idea is to use progressive training. This is particularly useful in the context of Earth observation, where we often work with different resolutions So one can think of training the GAN on the low resolution images and thus capturing the comparatively less complex low resolution data and eventually moving to higher resolution and thus progressively exposing the generator to learn more complex patterns. Think of this. How would you go for synthesizing hyperspectral data using GAN? So you, as we have discussed already, you'd have one generator, one discriminator, and the discriminator would try to discriminate whether this is a real data or a synthetic data, right? However, what all would be the inputs to this? Let us think a bit about this. Again, the input to the generator is the latent vector or the noise. Given this, the generator in this case is producing the synthetic spectra. We are talking in the context of the hyperspectral images, so we are calling this spectra synthetic spectra. Now, what about this particular part that we have still not kept? What is the other input to the discriminator, right? Let us look at this. That is simply the real spectra. This completes the simple GAN for synthesis of hyperspectral data, the real spectra and the generator generated synthetic spectra fed to the discriminator distinguishing between the real or synthetic spectra. Now, let us take a step ahead. Till now, what we have done, we simply had a generator, a discriminator. The generator is simply conditioned on the noise of the latent vector, right? And of course, noise and the latent vector, how to interpret this? Well, there are works in the literature towards that direction, but that's not what we are trying to discuss at this point. Rather, we are trying to understand that whether can we condition the generator on some additional input, some more meaningful input, let's say. So this leads us to conditional generative adversarial nets. Conditional GAN, that is simply adding additional condition input to the generator. Very often, this additional condition that we are talking about is the class. Like when we think about supervised data sets, right? What do we have? We have images and their corresponding classes, right? So that class information, like let's say building, road, vegetation, this class information, this is on what this conditional GAN most of the time is conditioned on. Thus, let us look a bit more from the perspective of the code or from the perspective of the algorithm to understand how would this work. So we still have z, our latent vector, and we will have an embedding corresponding to the label y embed. We call this label embedding given the class information or given whichever condition input we are using. Now the generator input is not just z, rather generator input is a combination of this z and y embed, which is now fed to the generator model. This generator input is fed to the generator model. However, the generator input is a combination of the z and the y embed. We will continue our discussion on generative adversarial network in the next lecture. Thank you.